And so the resulting curved pieces now indicate where stiffeners can actually go. Any stiffeners that are no longer positioned on these curves will automatically be repositioned. The plane definition will be stored as a user attribute inside a point object in Rhino. Again, in a separate grasshopper session, these planes, as derived from these points attributes, will be used to create curves to represent the shape of the stiffener object. These curves represent the nominal center line of the object at the top center. They do, however, at this point, not take into account the adjacent elements that they have to connect to. A grasshopper session uses filtering of geometry by attributes and some one to few closest geometry lookups to find the connecting elements. Trimming planes will be derived from these elements and stored as attributes again inside the wireframe curve. In the next session, these planes will be used to trim the actual curves. This is necessary for future steps where we need to create fabrication information and quantity takeoffs. As these trimmed curves are created in a new model, we still have access to the untrimmed curves from the previous step. Some processes may require the untrimmed curves instead of the trimmed ones. The stiffeners need to be mechanically fastened to the panel surface, and this is done by means of welded studs. The stud locations are defined in this stage and are represented by these green lines. A section profile needs to be oriented normal to the wireframe curve and panel surface. And also, whichever section profile that needs to be is also, again, stored as an attribute inside this wire. So Grasshopper already knows which section to take for each wire. So there's a plane that's also defined and saved as attribute on this wire. And then the section profiles are lying on this plane. And then these section profiles are extruded along these wires. Then we bring in all these trimming planes that we saved as attributes and we create trimming boxes on them. And these trimming boxes for all stiffeners are now again stored in wireframes as attributes. And the actual stiffeners are trimmed with these boxes. And the result is a fully attributed solid representation of a stiffener object. So the same principles are applied to all of the panels, also for the nodes. And this video illustrates the modeling process for all elements. So first we start with determining the panel joint locations based on rule sets and architectural intent. Then we trim away these joints in a separate stage. It's done automatically. Then these three-dimensional mean planes are used to set out this location of most of these grid lines. And then all of the framing elements will be modeled based on extensive rule sets. Primary framing, secondary framing, and everything is attributed. And then reference curves are created for each cardinal point of each rail. And we then model these trim boxes to make sure that we can trim away all excess of geometry. Then these surfaces are created, and then we're going to model these stiffeners as I explained in the previous example. Extruded, trimmed. Then we come in with brackets, and they're related to the steel connections that we modeled in previous stages. Primary brackets and secondary brackets. And this is all done in an automated fashion. Each of these steps is a separate Grasshopper file that we run in sequence. And we had people working on all these different definitions in parallel, because everything is basically based off of the same wireframes and the same input models. But most of these processes were done in parallel by many people. And so ultimately we have one panel completely modeled. And this is just one panel, of course. And so after all these models are generated, and this is only one panel, but this project, our scope basically consisted of almost 24,000 panels. So you can kind of imagine the amount of work it would have been to do this manually. It would have probably taken until the year 2028 to do that. So after all these models are generated, we need to make sure the models are correct before we send them off for fabrication. So our colleagues in New York have developed a live link between Grasshopper and our finite element analysis software, STRAND. And this is a bidirectional link that can have the frames analyzed for structural validity and bring the results back into the Grasshopper environment. And so by using this connection, we were able to validate all complex conditions under all load cases. And we also needed to make sure that the fabrication documents we were creating would actually result in the correct parts. So therefore we created Grasshopper scripts to interpret the information that we created from these models and use that information to recreate the parts in 3D and compare them to the parts that we modeled to make sure that everything would actually lead to the correct piece. So here you can see that we actually compare that recreated part against the model. And to make sure there are no obvious mishaps in the generated models, we would perform a visual checkup on each and every panel before we sent them out. And for this, we have developed a routine that will create a snapshot of each panel from a convenient perspective. And this bulk of images can comfortably be flipped through by a handful of people who will track any issues in an online spreadsheet. When all modeling work is verified, the next step is to produce the fabrication documentation for all the parts. I will show the stiffener first. In order to efficiently communicate the fabrication data for each stiffener to the fabricator, we created a diagram with variable dimensions for each possible combination of variables. An accompanying Excel file provides the exact values for the variable dimensions for each individual part. And next I will show you how the fabrication documentation for the aluminum sheets is created. The sheets are CNC milled after they have been welded to a CNC milled template. The template files are provided by us as 3D models of single surfaces. And the position of all elements is determined by the studs that are welded to the aluminum sheets. The locations of these studs need to be CNC defined. Therefore, we have to provide the locations as coordinates. But for verification purposes, we also need to produce a dimension drawing for each sheet showing all stud locations relative to the sheet edges. Then we take a few steps to find all these stud locations on the panel. And we add the locations to the provided CNC file. And the surfaces for the template are created automatically. The panel information is then in turn turned into a dimensioned 2D drawing that can be used to check all dimensions, as well as a 2D drawing to check all locations of the studs. So when all models are checked, all documents have been generated, and all parts have been fabricated, the panel needs to be assembled. All parts are labeled in the model, and an Excel file is created for each panel to describe which label refers to which part ID. And each labeled assembly will then be represented in a PDF that is accompanied by the generated Excel sheet. And this is what the assembly process looks like. And this process is performed for all parts, and all panels, on all members, and all nodes in the entire project. Resulting in an output of roughly 350,000 fabrication drawings and 150,000 assembly drawings, representing roughly 1 million parts. Unique parts, I must add to that. that is documented from a model consisting of over 3,000 Rhino models that were generated by over 400 grasshopper definitions. The project is currently under construction, and the facade installation is nearly completed. And so this talk is also nearly completed. And I want to explain that this talk is not really about bragging about this project or about how many parts we did. It is actually really about proposing a new way of modeling geometry and modeling data, and step away from the fact that we need files and models to exchange information. And I hope that we can think about how we could maybe utilize the cloud and and data exchange rather than file exchange for future processes. Thank you for your attention. Yes, absolutely. It was also a painful process at times because we created the shop drawings in a parallel process. The shop drawings were approved by the architect, and then we made sure that all of our fabrication documentation was actually according to the shop drawings. So the modeling team was basically modeling off of the shop drawings. Okay, so the question is, how do we distribute the tasks among the team? And the other question is, can we actually reuse some of the portions of the graph? And so distributing the tasks is basically, in this case, not too big of a problem because the team on this job was actually very small. I can say there were only 4 people working on this job. And so it took us about 8 months to get all of this work done with only 4 people. So I would say that attests to the process, but also you can imagine that it's relatively straightforward to manage a team of only 4 people, myself included, to get all this work done. So we would have just a big schedule on the wall and everyone would be assigned tasks, and we would have online task management systems for that. In terms of reuse, absolutely. We would be able to reuse a lot of this knowledge on different projects because the process is very strict. It starts with an envelope model and you take it all the way to a detailed fabrication model. And so we only do facades, so that makes it a little bit easier because facades consist of panels and each panel needs to be fabricated. So the process is very similar, and we would set up routines to reference and filter and structure our data and output them with pre-specified attributes, and all that we can just reuse in different projects. It's just only the middle part of each definition that's a little bit different, which is actually dealing with creating the geometry. But the rest of it is pretty much already set up. We've got scripts running for setting up folder structures, we've got scripts for setting up the models, the model names, accompanying work sessions, accompanying script files, etc. Also, all that is also automated. Okay, so the question is, why are we storing all this information in a 3D model instead of in a database? And it's a great question. And I would really like to take it there. At the time we started devising this process, and that's already years ago, we actually started off with a database, but we realized it was for us quite hard to define geometry in a database. And at that time we decided we cannot store the geometry in the database, we will store the data in the geometry base, basically. Currently, we're of course rethinking this strategy. At that time, we just needed to get the job done, and this was a way to do it, and it was working. I would really like to think about ways, and John already just talked about a little bit, about finding like a common ground, like a platform or a communication language to exchange not just data but also geometry on a neutral level between platforms, maybe to begin with, and maybe in its own platform in the future that could be accessed by anyone. So yeah, I hope that answers your question. I really hope to get there, and people are working on it. People are working on defining geometry in a neutral format for the cloud.